Okay, ladies and gentlemen, distinguished conference attendees, I'm delighted to present our research of the topic of methodology of measurement intellectualization based on the regularized Bayesian approach in uncertain conditions. This collaborative effort is authored by Svetlana, a professor and doctor of technical sciences from the Financial University under the government of Russian Federation, Veronika, PhD in technical science, deputy chairman of the Artificial Intelligence Committee of the RUSSOFT Association. In today's rapidly evolving landscape, the field of measurement theory has undergone a profound transformation. This transformation is driven by the increasing complexity of real-world problems that demands more sophisticated measurement processes and systems. Let's explore our current state and of affairs of this domain. Modern measurement tasks often involve complex hierarchical systems that exhibit dynamic properties influenced by the external factors. Unfortunately, direct measurements of such objects is often infeasible. Even the data is available, is frequently incomplete and inaccurate, leading to inherent uncertainty in measurement outcomes. This uncertainty is exacerbated by the diverse nature of information sources and data types. Some sources provide large volumes of data falling under the category of big data, while others offer the only small samples and unique experimental results. Furthermore, a significant portion of information relies on the expert assessment, adding another layer of subjectivity and complexity. One of the key advantages we face in the modern measurement systems is the absence of standardized technologies and for interpreting measurement results. This often leads to subjective interpretation, further contributes to the complexity of achieving accurate measurement. Additionally, there is a notable lack of comprehensive quality assessment and methodological support for measurement outcomes. This journey towards the intellectualization of measurement processes began in the 1980s and 1990s. Spearheaded by pioneers, researchers such as Dietrich Hoffmann, Leonid Finkelstein, Vladimir Rosenberg, and Svetlana. Their work laid the foundation of concepts like adaptivity in measurements, cognitive capability, and the intellectualization of measurement methods and systems. These early contributions, combined with prior research efforts, set the stage for the development in this vital branch of measurement science. It's important to recognize that at the time, existing information and measurement systems had limitations. Their algorithmic and object models were rigid, metrological support was insufficient, and they primarily addressed measurement situations with limited a priorized uncertainty, leading the oversimplified models of complex objects. These systems always struggled with the unified processing of numeric and non-numeric information, lacked algorithmic self-learning capabilities, and faced challenges in quality assessment and metrological support for measurement solutions. The introduction of processor-based measurement systems with substantial computational capabilities played a pivotal role in reshaping measurement intellectualization. The system facilitated the integration of new information technologies, enabled the amalgamation of various forms of incoming priori information to generate knowledge to optimize measurement strategies. This marked as an emergence of a unified measurement process. The conceptual framework of measurement intellectualization underwent further refinement, encompassing characteristics such as adaptability, modularity, computerization, automation, and architecture, self-calibration, explanation, and learning subsystems. Intelligence measurement found applications for modeling and decision support systems, firmly establishing their importance in a contemporary measurement science. In the modern era, measurement integration continues to evolve across several fronts. These include non-quantitative measurements, the expansion of measurement terminology, the utilization of artificial intelligence and soft computing, the metrology of intelligent measurements, and the adoption of Bayesian approach to foster intelligent measurement. The landscape now includes soft measurement as a prominent category. It's worth noting that the theory and principles of soft measurement were developed by Professor Svetlana in 1997. Currently, the methodologies and technologies of soft measurement are widely utilized in the practice of measuring and processing data from complex systems, significantly enhancing the quality and accuracy of measurement. As we delve deeper to our research of Bayesian intellectual and soft measurements, we will explore the contemporary developments and their implications. We look forward to sharing our findings and insights with you during this conference. Should I skip something because I joined a little bit later or not? Okay, the evolution of measurement theory towards intellectualization has been driven by the increasing complexity of practical problems. To appreciate this journey, we must acknowledge the pioneers of researchers who paved this way. During the 19th, the Second International Measurement Consideration Symposium in Germany played a significant role in advancing the field. It was during this event that the term intelligence measurement was first coined by Dietrich Hoffmann and Leonid Finkelstein, solidifying the concept of intelligence measurement. An essential catalyst of the intellectualization of measurement systems was the incorporation of processor-based tools and substantial computing capabilities. These technologies allowed the computerization and automation on measurement processes, ushering in the era where optimal measurement strategies could be developed automatically based on various forms of incoming and prior information, representing the essence of measurement intellectualization. As we reflect on historical trajectory, it becomes evident that the roots of intelligent soft measurements stretch back several decades. The intellectualization of measurement theory has continued to evolve, branching into various directions, including quantitative measurements, systematization of measurement terminology, non-physical measurements, and integration of artificial intelligence and soft computing methodology of intelligent measurement, and the application of Bayesian approaches to create methodologies for intelligent measurement, including soft measurement. In essence, the explanation of our research is a continuation of this rich history. Today, we stand on the shoulders of these pioneers as we embark to a journey to advance in the field further and address its current challenges and opportunities. Now, having explored the historical underpinning and key figures in the field of intelligence and soft measurement, let us turn attention to our current state. In doing so, we embark a critical review aimed at identifying shortcomings and existing landscape, while also proposing novel approach and methods. I really asked my colleague, Dr. Svetlana, say if I need to skip something in this part, because we will explain more in detail our formulas and our approach. Okay. Regrettably, the lack of robust interpretation technologies, modern measurement systems can lead to a subjective interpretation, including additional uncertainty. Moreover, there is often a dearth of quality assessment and metrological support for measurement solutions. They need for intelligence measurement methodologies became evident as a shortcoming of existing system, because they became increasingly apparent. The journey towards intellectualization began in the late 20th century, but many of the change identified as persist today. Existing systems are often characterized by rigid algorithmic structures, insufficient methodological support, and technogenic focus that oversimplifies complex objects. The introduction of computation modules into measurement environments characterized by modularity and adaptability marked a turning point in the field. This advancement led to the automation and computerization of measurement processes, fundamentally altering the measurements are conducted. Intelligence measurement technologies now encompass fully realize the potential of intelligence measurements. We require well-developed user interfaces and open standardized software and hardware subsystem for metrological support and self-calibration capabilities. These systems also feature explanation and learning subsystems find application in modeling and designing support systems. When navigate to complex landscape of intelligence and software measurement and soft measurements, we must embrace the wealth of concept and methodologies. These include not quantitative measurements, expansion of measurement terminology, and measurement of non-physical quantities, integration of artificial intelligence of computing, metrological consideration, and the application of Bayesian approach. These components collectively contribute to the ever-evolving realm of intelligent and soft measurements. So let's delve the methodological aspects of our approach. This section outlines the guiding principles and metrological that underpin our work to the realm of intelligence measurements. First and foremost, our approach rooted in the philosophy of holistic measurement. We recognize that intelligence measurements extend beyond mere data collection. They encompass a comprehensive understanding of the measurement object, its environment, and the context of the measurements are taken. Our methodology emphasizing the integration of diverse knowledge sources, ranging from empirical data to expert insights, and to create a more complete and accurate picture. A key tenet of our approach is consideration of uncertainty. We operate and in an environment where complete information is often elusive. Therefore, our methodology is designed to thrive in conditions in considerable uncertainty. Rather than shying away from uncertainty, we embrace it in an inherent aspect or intelligence measurement. To address uncertainty, we employ advanced information technologies and statistical techniques. This enabled us to derive measurement solutions from imperfect, incomplete, and sometimes contradictory information. Our approach aligns with the principles of Bayesian statistics, where we consider the probabilities of various hypotheses to arrive at robust measurement solutions. A fundamental aspect of our methodology is to use dynamic models. These models evolve in response to new information, continuously adapting to better represent measurement object as its surroundings. Their adaptability ensures that our measurements remain relevant and accurate even as conditions change. Moreover, our methodology incorporates principles of cognitive science. We recognize that measurements are not isolated events, but rather components are broader cognitive process. As such, our approach places a strong emphasis on the cognitive functions involved in measurement, including perception, reasoning, and decision-making. In practical terms, our approach results in what the term comprehensive measurement solutions. Their solutions encompass not only numerical values, but also various forms of information representation, including linguistic description, graphical data, and expert assessments. By considering multiple phases of information, we create a more holistic and insightful view of the measurement. As a result, our approach offers a nuanced understanding of measurement quality. Traditional metrics like accuracy and precision are augmented by indicators of reliability, conducting accuracy, and the level of information entropy. These comprehensive metrological characteristics provide a more robust basis for decision-making and complex, uncertain measurement scenarios. In summary, our methodological aspect to intelligence measurements exhibit adaptability, cognitive foundations, and resilience in the face of uncertainty. By adhering to these principles, we aspire to advance the front lines of measurement science and offer valuable insights and the educate to specific phenomena. In the realm of intelligence measurements, modern information technologies play a pivotal role of dealing with complex, uncertain measurement tasks. These technologies are applied. Probabilistic logic and Bayesian approach. We rely on probabilistic logic and the Bayesian approach to integrate prior knowledge with incoming information, yielding probabilistic measurement solutions. This approach excels situations fraught with uncertainty. Dynamic, compact solution space. DCSS is the heart of our methodology. It involves breaking down the solution space into two-dimensional metric space, accommodating different object properties and their probabilities. DCSS is highly adaptable to changing information and evolving situation. Scale and dynamic constraints. SDC is instrumental and intelligent measurements. It's a flexible scale for that adjusts its properties based on changes in the underlying measurement models. This adaptability is crucial for meeting dynamic measurement needs. Convolution of information. We employ information technologies to combine various types of data, including numerical and linguistic information, and the probabilistic in a probabilistic manner. This integration helps us to handle uncertainty effectively. Linguistic variables for measuring qualitative indicators, we utilize linguistic variables on a linguistic scale. Information technologies assist in interpreting solutions, aligning with specific measurement goals, especially when numerical data falls short. Parametric logics in the realm of soft measurements will leverage parametric logic such as those introduced by Zade and Lukashevich, and information technologists support the application of this logic in imagining complex uncertain data. Pattern recognition. We employ pattern recognition principles, treating measurement results as patterns. Information technologies play a vital role in identifying these patterns, where images represent reference points on the measurement scale. Modifying Bayesian approach. Our methodology incorporates a modified Bayesian convolution formula to ensure the reliability of measurement results when integrating numerical and linguistic data. Information technologies enable the effective implementation of this approach. Hypercube of interrelated factors. When multiple indicators are involved, we construct a hypercube interrelated factors with a multidimensional parameter space. Information technologies facilitate the management and interpretation of this multidimensional space. Cognitive measurements. Information technologies are seamlessly integrated in the cognitive measurements, where the subject of measurement interacts with the measurement system as a source of receiving information. These technologies support the dynamic models adaptation of changing information. It's essential to note that Professor Svetlana Prokofievna pioneering cognitive measurements in 2007 and remains a leading authority in this field. In summary, modern information technologies are backbone of our methodology, allow us to excel the complex measurement scenarios characterized by uncertainty and evolving requirements. These technologies facilitate data integration and adaptability and ensure the reliability of our results. Dr. Svetlana, would you like to present next two slides?
Yes, of course, I can do it and to help you. This is the main formulas connected with the receiving solution in the form of a priori and a posteriori probability of the estimation of our factor. The first one is the classical one formula by Bayes, but two others, the modification of this approach under condition of uncertainty, when we haven't knowledge about low probability, and when we have incomplete and a small sample information, as well as linguistic and numerical. The Thorstvedt formula is more common formula for data processing. All kinds of information about complex object and environment. I mean the factors which are influence on factor of complex object. And so this formula allows us to processing data under the complex condition with various type of logic. For example, soft logic, Zade, strict logic, Lukashevich, and probability logic, Bayesian logic. So we have a lot of possibilities to combine together, to integrate together all kinds of information about complex object and environment. And in each step, after calculation, the estimation of value of factor, we have the possibility to have a metrological characteristic of this solution in the form of accuracy, validity, dependability, and so on. And after that, we have the step-by-step possibility to do our process transparency. It's one of the, it's one of the problem of artificial intelligence just now, to have a solution under condition of transparency. Then we have the possibility to interpretate of this solution, and so this is explainable artificial intelligence. This is the second problem of modern artificial intelligence science. And we have a possibility to develop our solution, to receive our solution in various form. Just now, I would like to give the possibility to continue presentation of my colleague Veronika Zaslavskaya. This is exactly the illustration of scale with the dynamic constraints and the results of dynamic models in fuzzy form. So we have, you see, two parts of scale. One part connected with numerical data, and second one connected with linguistic decision. And we have, for example, values, a set of values with probability for each alternative of this solution, and plus we have interpretation in linguistic form, norm, below norm, and so on. It's give us the possibility to have a most complete solution. So thank you so much. And Veronika, would you like to continue your presentation?
Yes, sure. As we move forward in the digital age, BIM is playing a critical role, bringing cutting-edge IT trends with measurement, offering the enhancing decision-making capabilities. First of all, our list of remarkable potential of BIM boosting and stability of profitability of small businesses. The applying of principles of BIM, we can only assess the business situation, but also create digital twins of small enterprises. These digital twins can greatly enhance probability, create a more comfortable working environment for employees, and improve overall competitiveness in the market. Moving on, we have a real-world example right here in Moscow, where Professor Svetlana Prokopchina is living the hot water supply network control. BIM has effectively integrated into this system, incorporating multiple neural networks. This fusion of Internet of Things with artificial intelligence has resulted a more resilient and efficient water supply network, demonstrating how BIM can bring value to critical infrastructure. Finally, let's talk about using BIM in sustainable regional development. It involves factors like demographic, economics, and more. By harnessing BIM, we can create data-driven strategies to enter regions' sustainable growth, making use of IoT and AI to achieve economic and social development goals. Okay, conclusion. In conclusion, we find ourselves at the intersection of cutting-edge technology trends in the IT industry, including IoT, big data, data science, and BI. These trends involve the connection and processing of diverse data streams, often originating from complex real-world systems. These systems pose unique challenge due to their unpredictability, inaccessibility for direct observation, and fundamental unknowability. To address these challenges, we explored the regularizing Bayesian approach, RBA, and Bayesian intelligent measurement, BIM technologies. Their approaches have proven variable of situation of information uncertainty, where traditional measurement methods fall short. By incorporating additional information about the object being measured and the factors influencing them, we can obtain not a single precise solutions, but a range of alternative solutions. This approach reduces uncertainty by leveraging a spectrum of possible outcomes. Looking ahead, the prospects for applying BIM and methodologies are promising. They align with various emerging areas of artificial intelligence and data science. Here are some key areas of potential applications. Data science, based on intelligent measurement system, can play a role in metrologically sorting data and knowledge flows, facilitating their integration and enhancing data quality. IoT, BIM can be integrated into Internet of Things systems to collect, integrate, interpret, and instrument data, enabling more robust decision-making. Business intelligence, BIM offers analytical capabilities for processing and interpreting information, making it valuable for BI systems. Neural networks, BIM can be used to certify and integrate data to knowledge when training neural networks, enhancing their learning processes. Big data, BIM can help reduce dimensionality of big data, making it more manageable and meaningful. Mathematical and analytical processing. BIM is particularly useful for handling uncertainty for small sample sizes and mathematical and analytical processing. Complex system management. BIM and SM can be applied to monitor and manage complex industrial and social economic systems, contributing to their sustainable development. The integration of measurement methodologies with intelligence approaches represent an exciting step in the evolution of measurement theory and artificial intelligence. It enables us to tackle complex problems in the ever-expanding landscape of data and technology, offering new opportunity for innovations and discovery. Dear conference attendees, we appreciate your interest in our presentation on the regularized Bayesian approach. methodology and its applications in the field of intelligence measurement. If you have any questions or comments, or you need more detailed information about RBA and our research, please feel free to reach out to us. You can contact me and Professor Svetlana Prokopchina, renowned author of 9 monographs and over 200 scientific works. We would be delighted to answer your questions, discuss the potential applications of RBA in your area, and provide additional information about this unique methodology. As I concluded the presentation, we would like to express our gratitude to your attention and participation, and believe that RBA can make a significant contribution to the field of measurement science and artificial intelligence. Please don't hesitate to get in touch, and we look forward to productive collaborations in the future. Thank you. Best wishes for a successful conference.